You jump into a hole in the ground, gravity grabs you, and you don't stop falling for nearly 40 minutes, shooting through rock, molten iron, and temperatures hotter than the surface of the sun. The wild part? The physics actually work. Let's go. From core to sky, today we take the express route. Okay, so here's the scenario. Someone, let's say a very confused person, or a very brave person, depending on the perspective, finds a perfectly drilled tunnel that goes straight through the center of the Earth. Pole to pole, they walk up to the edge, they look down, and Geronimo! What happens next is one of the most mind-bending rides physics has ever cooked up, and we're going to follow them the whole way down. But first, real quick, let's talk about why this question even matters. Because it's not just a fun daydream. The gravity tunnel problem is a staple of introductory physics courses because it simultaneously demonstrates striking features of the Newton's law of gravity and a very important type of cyclical motion. Physicists have been arguing about the answer for decades, and spoiler, the answer most people got taught for 50 years turned out to be wrong. We'll get to that, but first, let's actually build this tunnel because the engineering alone is already insane. The tunnel problem. The deepest humans have ever drilled is just over 12 kilometers, which is about 7.6 miles below the surface, and even that took 20 years. That was the Kola Super Deep borehole dug by the Soviet scientists in Russia starting in 1970. And here's the humbling part. While the Kola Super Deep borehole never reached beyond Earth's crust, it remains the deepest hole ever dug. We scratched the skin of an apple and called it a win. The hole is only 9 inches in diameter, about 23 centimeters, so it's not even like a proper hole. It's basically a straw poking into the ground. And the Soviets were forced to give up when they hit unexpectedly high temperatures, around 180 degrees Celsius at just 7.5 miles down. That's almost twice what they predicted. The drill bits warped. The rocks at those depths behaved more like plastic than rocks, to be honest. And that's just 12 kilometers into a planet that's 6,400 kilometers to the center. So, our hypothetical tunnel? The full distance would span more than 12,000 kilometers, about 7.5 thousand miles. It's absurd. It's impossible. It's perfect. Let's do it anyway. Before we take the deep dive, though, I just want to share this program with you that I found recently that has helped me a lot with finding mental clarity, relaxing, and focusing on tasks, such as making these videos. It requires deep research, so it has helped me a lot, and I thought it might help you as well. Link is in the description, also in the pinned comment. Worth a look. But before we jump in, you need to understand what's actually waiting for you down there, because every layer of this planet is trying to kill you in a different and increasingly creative way. The layers of doom. Let's walk through what our brave or deeply confused diver would pass through. First up, the crust. This is the bit we live on. It feels massive when you're hiking a mountain, but in the grand scheme of the planet, the crust is only about 3 to 5 miles thick under the oceans, and about 25 miles thick under the continents. Like the shell of an egg, the Earth's crust is brittle and can break. It's the thinnest, most fragile layer, and we've been living our entire civilization on it, completely unaware of what's underneath. Now that's just cute. As you punch through the crust and hit the mantle, things get immediately worse. Below the crust is the mantle, a dense, hot layer of semi-solid rock approximately 2,900 kilometers thick. It's hotter and denser because temperature and pressure increases with depth, and the scale of it is wild. The mantle is about 2,900 kilometers, which translates to about 1,800 miles thick, and makes up a whopping 84% of Earth's total volume. So you've been falling for a while now, and you're still mostly in the mantle. The temperature is climbing fast. The temperature of the mantle varies greatly from 1,000 Celsius, which is about 1,832 Fahrenheit, near its boundary with the crust, to 3,700 Celsius. That's about 6,692 Fahrenheit, near its boundary with the core. That's not a typo. 3,700 degrees Celsius at the bottom of the mantle. You're not cooked. You're vaporized. You're a concept. You exist in memory only, basically, at this point. But let's say our diver has a miraculous futuristic suit, the kind that laughs at pressures and heat and... Look, we're doing the physics here, not the obituary. They keep falling, alright? And here's where it actually gets strange, because the outer core, it's not even solid. It's a sea of liquid metal, the metallic ocean. The outer core is made of mostly liquefied iron, nickel, and other elements that made molten by the extremely hot temperatures found there. Our diver is now plunging through a spinning ocean of liquid iron at thousands of degrees. This ocean, by the way, is also the reason your phone's compass works. Magnetic fields generated by the Earth's core protect Earth from solar radiation. So next time you use your GPS, quietly think the liquid metal spinning 3,000 kilometers beneath your feet. And then, the inner core. That's what we talked about in the previous video. This is the wildest part of the whole planet. Temperature in the inner core is about 5,200 Celsius. That's almost 10,000 Fahrenheit. Exactly 9,392. I do like to exaggerate a bit. But let's keep moving along. The pressure is nearly 3.6 million atmospheres. For reference, the surface of the sun is about 5,500 Celsius. So you are, give or take a few hundred degrees, falling through something that is as hot as the bloomin' sun, except compressed to an almost unimaginable degree. And yet, the inner core is solid. It's made mostly of iron, but the atoms are under such immense pressure that they lock into a solid regardless of the temperature. It should not be a solid at that heat, but the pressure is so extreme it just forces everything to stay together, like trying to squish a marshmallow until it turns into metal. Except the marshmallow is iron and the squishing is 3.6 million atmospheres. Did you hear that, people? That's absolutely insane. The inner core is slowly growing as the Earth cools by a few millimeters each year. A fun fact for your next dinner party that will make everyone slightly uncomfortable. Okay, so our diver has made it through hot rock, a liquid iron ocean, and a solid metallic core hotter than the sun. Now comes the weirdest moment of the whole trip. Zero gravity at the center. The strength of gravity at the center of the Earth is zero, because there are equal amounts of matter in all directions, all exerting an equal gravitational pull. Think about that. You're at the center of a planet, 6,400 kilometers of rock in every direction, and you feel completely weightless. You are, for just a fraction of a second, floating in the middle of the world, literally, during the entire fall. You'd experience complete weightlessness, identical to what astronauts would experience on the ISS. This is because you're in free fall, the same physics that makes skydivers feel weightless before their parachute open. But here's the catch. You're not stopping here. The small amount of momentum you have at that point causes you to overshoot the center of the Earth and keep moving. But once you're past the center, down is now the other direction. So you slow down. See what I did there? It's exactly like being a pendulum. You swing down, you hit the bottom, momentum carries you up the other side, gravity pulls you back. Swing and repeat. How fast are you going? Well, let's talk speed, because this is where the numbers get genuinely ridiculous. If you jumped into the tunnel, you'd fall down towards the center of the Earth, accelerating constantly thanks to gravity. By the time you reach the halfway point, after falling for about 21 minutes, you'd be traveling at 28,000 kilometers per hour. That's 28,000 kilometers per hour. That's roughly 17,400 miles per hour. That's faster than the International Space Station orbits the Earth. You have become briefly and spectacularly a human meteor. Once you cross the halfway point, the velocity would carry you back up the other side for another 21 minutes. This time, gravity is slowing you down, so by the time you reach the other end, you come to a perfect stop, just as you arrive. It's perfectly symmetrical, no fuel, no engine. The trip didn't require any energy. You exchanged gravitational potential energy for kinetic energy on the way down, and then exchange it back on the way up. The universe basically gave you a free ride through the planet. Now, here's where it gets interesting, because how long does the trip actually take? And this is where physicists have been quietly arguing for years. The 42-minute debate. The answer taught for nearly half a century for how long a fall through such a hole would take was about 42 minutes and 12 seconds. That's the classic textbook answer. It's been in physics classroom for decades. It's probably the answer your teacher gave you, and mine as well. But here's the problem. The usual calculations make an unrealistic assumption that, like a billiard ball, Earth has the same density throughout. In that case, the strength of the gravitational force pulling you towards the Earth's center varies in proportion to your distance from the center. Earth is not a billiard ball. The core is enormously denser than the crust. So a physicist named Alexander Klotz at McGill University decided to redo the math using real seismic data and the actual measured density profile of the Earth. Numerically, it was found that the time taken to fall along the diameter is 38 minutes, compared to the 42 minutes for a planet with uniform density. As Klotz explains it, and I quote, "The way the Earth is structured, the gravity increases slightly as you go deeper towards the dense core, to about 110% of its surface value, before getting weaker as you move through the core, reaching zero at the center." End quotes. So the denser core actually pulls you faster through the middle of the trip. You get there in 38 minutes, not 42. 4 minutes might not sound like much, but in physics, being off by 4 minutes on a calculation you've been taught for 50 years is a massive deal. Textbooks are still catching up. And here is the beautiful kicker that Klotz also discovered. For a tunnel that reaches from one point to another point on the Earth's surface but does not pass through the center of the planet, the travel time would still be about 42 minutes. Any cored tunnel, New York to London, Sydney to Tokyo, all of them, 42 minutes. The geometry works out the same every time. This concept is what physicists called a gravity train, and it has inspired real proposals for gravity trains between nearby cities using shorter, shallower tunnels, especially a high-tech roller coaster. But wait, what happens if you don't have the perfect vacuum tunnel? What if there's air? The air problem. Here's the nightmare scenario. If you fill the tunnel with air, normal, regular air, the physics goes catastrophically wrong. The tunnel needs to be a complete vacuum. If there's air, you'd fall at terminal velocity, and you'd end up stuck at the center of the Earth, completely weightless and completely helpless. Imagine falling for 21 minutes, slowing down as the air gets thicker and denser until you're just floating, suspended at the center of the planet, not moving, can't go up, can't go down. The air pressure at the center would be absolutely crushing. The air in the hole at that point is so dense that it is like traveling through soap. You'd be the world's most geologically inconvenient person, stuck at the center of the Earth, no way out. This is why the thought experiment requires a vacuum and why Klotz joked about it. And I quote, "In my opinion, if you have the technology to dig such a tunnel, you have the technology to suck the air out." End quotes. Fair point. The rotation problem. There's one more wrinkle that most people miss. The Earth is spinning, if you haven't noticed. Well, it's kind of hard to notice from here, but it is spinning, as we have learned. And that creates a huge problem for our very confused or brave tunnel diver, depending on who you are. Earth's rotation would push the falling object against the tunnel walls due to the Coriolis effect, requiring magnetic levitation or a curved tunnel to compensate. So for the gravity train to actually work, the walls of the tunnel would need to support you magnetically, like a giant underground maglev track. You'd be floating through a tube at 28,000 kilometers an hour guided by magnets through the center of the Earth. At that point, it's not really falling through the Earth anymore. It's more extreme transit system ever conceived. Tokyo to Sao Paulo, 42 minutes, no fuel, just Newton's best friend, the gravity. The real-world reality check. Now, a reality check, because we are a science channel after all, however whimsical I might sound. Upon falling to about 200 kilometers deep, just 3% of the way to the Earth's center, the temperature reaches about 1,200 Kelvin, which is hot enough to incinerate everything. No suit we have today comes close to surviving that. The deepest we've ever drilled, the Kola Super Deep Borehole, reached 40,230 feet, which is about 12,262 meters in 1989. And it stopped not because they wanted to, but because the rock started behaving like plastic, and the drill pipes literally began stretching like rubber under the immense stress. We got to 12 kilometers into a 6,400 kilometer journey, and the planet basically said, "Nope, not happening. Not today, buddy." back off. But here's why this thought experiment matters beyond just the cool physics. It tells us something profound about the gravity works. That it's not just a force pulling you down, but a force that decreases as more and more mass gets above you. It's the shell theorem. As you descend, the amount of mass at an altitude lower than yours decreases, whereas the mass above you no longer affects you. You're pulled only by the sphere of the Earth beneath your feet, and that sphere shrinks with every meter you fall, and the result is this perfectly elegant oscillation, because the force pulling you towards the center is proportional to your distance from the center. The further you are, the stronger the pull, and the closer you get, the weaker it becomes. This system behaves exactly like a spring. In fact, the math is identical. It's called simple harmonic motion, and it's the same equation that describes a pendulum swinging, a guitar string vibrating, or a kid on a playground going back and forth on a swing for what feels like 400 years. Nature found one elegant equation, and she uses it everywhere. The universe is lazy like that. Efficient. We love to see it. So our diver doesn't crash into anything. They don't explode at the center. They just oscillate back and forth, pole to pole, forever, in a perfect, frictionless vacuum, like the universe's most dramatic metronome, taking through the center of the Earth for eternity, 42 minutes each way, 84 minutes per full cycle. And here's the part that genuinely gives physicists the warm fuzzies. That 84-minute orbital period, it's the exact same time it takes a satellite to orbit the Earth at ground level, if the ground weren't in the way, that is. The gravity tunnel and the low Earth orbit are mathematically the same system. One goes around the planet, the other goes through it. Same equation, same period, same universe, being unreasonably elegant about the whole thing. So let's zoom out for a second, because what does all of this actually tell us? What it all means? This thought experiment isn't just a physics party trick. It's a window into how gravity actually behaves. Not a constant downward tug, but a dynamic, depth-sensitive force that weakens as you descend, hits zero at the center, and rebuilds on the other side. It tells us that the Earth isn't just a rock we live on. It's a gravitational machine, a perfectly tuned system where mass, density, rotation, and energy exchange all are speaking the same mathematical language, and have been since the planet formed 4.5 billion years ago. And the next time you're stuck in traffic, commuting 2 hours to 30 miles, just remember, in a perfect world with enough engineering budget and a total disregard for whether something is technically possible, you could cross the entire planet in 38 minutes for free, powered entirely by Newton's best friend, the gravity. We just need to drill 12,000 kilometers through the hell first. Easy. And so that's what happens when you take a one-way ticket through the planet. Turns out physics gives you a return ticket for free. From core to sky, this Earth never stops surprising us. If you want more of the universe being quietly, outrageously clever, stick around and we've got plenty more ground to cover. Literally. And if you made it this far, thank you so much, first of all. And secondly, I mentioned a program earlier that has helped me a lot in focusing when doing research for these videos and also relaxing afterwards. And I've left the link to that in the description down below, as well as the pinned comment, so check it out if you're interested in that sort of thing.